Today we will discuss the calculus of the natural logarithm, and the first step is to calculate the derivative of log x. Now to do this, what we're going to use is the fact that f of x equals e to the x and g of x equals log x are inverse functions, and that we know the derivative of e to the x, namely e to the x. So what we do is we write f of g of x equals e to the log x, which we know, because these two things are inverse functions, is x. And it's that expression that we're going to differentiate to find the derivative of the log. Okay, so let's look at f of g of x prime. That's a chain rule calculation. F prime of g of x times g prime of x. Now f prime of x is e to the x, so that becomes e to the g of x times g prime of x. And g of x is log x, so this becomes e to the log x times the log of x prime. Now, e to the log x is x. So that entire thing becomes x times the derivative of the log x. And that's the derivative of this expression, which is this expression. Now, the derivative of x prime is 1. So when we plug that in, we get x log x prime equals 1. And as a result, when we divide through by x, we get the log of x prime is 1 over x. And that's the derivative of log x. Derivative of log x is 1 over x. And it's important to note this is for x greater than 0, because the log of x does not make sense when x is negative or 0. So, for example, let's calculate the derivative of x cubed log x. This is just a standard product rule. So it's going to be the derivative of x cubed, which is 3x squared, times log x, plus x cubed times the derivative of log x, which is 1 over x. And x cubed times 1 over x is x squared. So we end up with 3x squared log x plus x squared. Now, how about a more complicated situation where we're taking the log of a function? Let's see what the derivative is. So again, we're going to do a chain rule. Think of g of x as log x. And we know at this point that that means that g prime of x is 1 over x. The log of f of x is g of f of x in this notation. And when we use the chain rule, we get the log of f of x prime is g prime of f of x times f prime of x. G prime of x is 1 over x. So we end up with 1 over f of x times f prime of x, and that's our rule for differentiating the log of a function. The derivative of the log of a function is 1 over that function times the derivative of the function. So let's do an example. Let's calculate the derivative of the log of the sine of x. So according to what we see here, that should just be 1 over sine x times the derivative of sine x, which is cosine x. A more complicated example, let's calculate the derivative of the log of x cubed plus 1 over x squared plus 1. Now this is obviously a quotient, so we're going to use the quotient rule. And we're going to get denominator times derivative of numerator, which I'm just going to leave now as the log of x cubed plus 1 prime, minus the numerator, log of x cubed plus 1, times the derivative of the denominator, which is 2x, over denominator squared. Now what's left is to calculate the derivative of the log of x cubed plus 1, and according to what we've done up here, that should be 1 over x cubed plus 1 times 3x squared. And this whole expression is the derivative of our original function. Now, let's calculate the derivative of the log of x squared sine x plus 3 cubed over x cubed plus 1 cubed. Now, this looks like it might actually be pretty horrible if we use this expression, because we would have 1 over this mess times the derivative of this thing, which is going to be a complicated quotient rule that will involve a product rule, which will involve a chain rule. But in this situation, it makes sense to simplify the expression before we calculate the derivatives. So y here is this log, and it's the log of a over b. So we know from properties of logs, that's log a minus log b. And now we can simplify these individual pieces. This is the log of a product, so it's going to be the log of x squared plus the log of sine x plus 3 cubed. This is the log of something to a power, so that power comes out in front. And then finally, we can use that power rule on these other two terms, and we can get the log of x squared turning into 2 log x, the log of sine x plus 3 cubed turning into 3 log sine x plus 3. And now we're going to differentiate this expression, which is actually pretty easy. The derivative of log x is 1 over x. The derivative of the log of sine of x plus 3 is 1 over the sine of x plus 3 times the derivative of the sine of x plus 3, which is cosine x. And the derivative of the log of x cubed plus 1 is 1 over x cubed plus 1 times the derivative of x cubed plus 1, which is 3x squared. And that's a much easier calculation than would have been if we hadn't done the simplification first. Now let's talk about antiderivatives. We know that the derivative of the log of x is 1 over x when x is bigger than 0. And as a result, the antiderivative of 1 over x is log x plus c when x is bigger than 0. But what about 1 over x dx when x is less than 0? The problem here is 1 over x exists when x is negative, but log of x does not. So we're going to need something to handle those cases. And it turns out that what's going to do the job for us is the log of absolute x, which is log x when x is greater than 0, and the log of minus x when x is less than 0. We already know that for x greater than 0, the derivative of the log of x is 1 over x. Now we have to worry about what's happening when x is less than 0. And if you take the derivative of the log of minus x using chain rule, it's 1 over minus x times the derivative of minus x, which is minus 1. You multiply everything out, and you get 1 over x. So the derivative of this is 1 over x, which means for all x not equal to 0, the derivative of the log of absolute x is 1 over x, and that turns out to be our answer. The antiderivative of 1 over x dx is the log absolute x plus c, and that handles the case when x is negative as well as when x is positive. So here's our formula. Antiderivative of 1 over x is log absolute x plus c, and that's obviously true anytime x is not 0. So let's do an example. Indefinite integral 1 over 3x plus 2 dx. Okay, so we're going to make a substitution. U equals 3x plus 2. So du dx is 3. Du is 3 dx. We only have a dx in the integral, so we divide through and we get 1/3 du equals dx. We substitute. 1 over 3x plus 2 dx is 1 over u times 1/3 du. We know how to antidifferentiate here. We get 1/3 log absolute u plus c, and now remember that u is 3x plus 2, so we've got 1/3 log absolute 3x plus 2 plus c. Notice here that we do need the absolute value signs to take care of the case when the x values make this expression in here negative. Let's do another example. Find the antiderivative of x over x squared plus 4. Now in this situation, it makes sense to think about substituting u equals x squared plus 4, and the derivative is going to be 2x dx. There's an x around, so this has a good chance of working. So u equals x squared plus 4. Du dx is 2x. Du is 2x dx. There's an x dx in the integral, so we divide through by 2 and get 1/2 du is x dx. And now we just substitute. X dx is your 1/2 du. 1 over x squared plus 4 is your 1 over u. We know how to find an antiderivative. It's going to be 1/2 log absolute u plus c. And remember that u is x squared plus 4, so we get 1/2 the log of absolute x squared plus 4 plus c. Now this is a perfectly good answer, but let's notice here that x squared plus 4 is actually always bigger than 0. So if we wanted to, we could pull off the absolute value signs and just write it as 1/2 the log of x squared plus 4 plus c. Let's do another example. The log of x to the 4th divided by x. Now, it may not be so obvious what to do here, but we do have this composition of functions, the log of x to the 4th. So it makes sense to think about substituting for log x, and the derivative of log x is 1 over x, and that's in the integral. So we're going to make that substitution. U equals log x, du dx is 1 over x, which means that du is 1 over x dx, which is in the integral. So when we substitute, the log of x to the 4th becomes u to the 4th, dx over x becomes du, and now this is a very easy integration. We just get u to the 5th over 5 plus c, and we remember that u is log x, so we get log of x to the 5th over 5 plus c. Let's look at one more example here. E to the x divided by e to the x plus 3. Now, it may not be so obvious what to try here, but notice that if we were to substitute for e to the x plus 3, the derivative would be e to the x, which is in the integral. So that's what we're going to try and do. U equals e to the x plus 3. Du dx is e to the x, which means that du is e to the x dx. And now we can transform this integral. E to the x dx becomes your du. 1 over e to the x plus 3 becomes 1 over u. And now we just get the natural log of u plus c. And remember that u is e to the x plus 3, so we get the log of absolute e to the x plus 3 plus c. And again, a perfectly good answer. But remember that e to the x is always positive, which means what's in here is always positive. So if we wanted to, we could remove the absolute value signs and just write the log of e to the x plus 3 plus c.